Hey, quick question. What scares you more, outer space or what's sitting at the bottom of our own ocean? Because here's the thing. We've mapped more of Mars than we have of Earth's ocean floor. More of Mars. We sent people to the moon in 1969, but the deepest place on our planet? We visited it fewer times than humans have walked in space. That place is called the Mariana Trench. It's nearly 11 kilometers straight down, and what scientists found there didn't just surprise them. It broke basically everything they thought they knew about life itself. We're talking creatures that survive pressure that would crush a submarine like an empty soda can, ecosystems that run on chemistry instead of sunlight, microbes that may have been quietly living down there since before the dinosaurs showed up, and are still going. This isn't science fiction, this is your planet, and it's way weirder than anyone gave it credit for. Before we dive in, literally, smash that like button if you're into this kind of stuff because it genuinely helps. And drop a comment right now. Where in the world are you watching from? I want to see how far this one travels. Alright. Let's go down. Most people have heard the name. It floats around in documentaries, in science class, in those late-night rabbit holes where you end up questioning everything you thought you knew about the planet you live on. Mariana Trench. Sure. Deep place? Got it. But here's the thing. Knowing the name and actually grasping what it is are two completely different experiences, and almost nobody has the second one. So let's fix that right now, because the scale of this place is the kind of thing that rewires your brain a little. Let's start with location, because geography matters here. The Mariana Trench sits in the western Pacific Ocean, east of the Mariana Islands, hence the name, not exactly a creative committee at work there, and it curves in a long crescent shape across the ocean floor. We're talking about a feature that stretches roughly 1,500 miles from one end to the other. For context, that's longer than the entire state of California top to bottom, multiplied by about 3. You could fit the entire Appalachian mountain range inside this trench lengthwise and still have room left over for a couple of small European countries. It is not a hole, it is not a crack, it is a scar on the face of the planet, and it is enormous. But length is almost the least impressive thing about it. The depth is where your brain starts to short-circuit. The deepest known point in the Mariana Trench, and in the entire world ocean, is called Challenger Deep, named after the British naval vessel HMS Challenger, whose crew first measured it back in 1875 using a method that basically involved dropping. A weighted rope overboard and waiting. Unglamorous? Sure, but it worked well enough to reveal that something very unusual was going on down there. Today, with modern sonar and submersible technology, we know that Challenger Deep reaches approximately 10,935 meters below sea level. Round numbers are often easier to work with, so let's just say nearly 11 kilometers, nearly 7 miles straight down. Now those numbers are impressive on paper, but they don't really hit until you stack them against something familiar. Take Mount Everest, the tallest mountain on Earth, standing at about 8,849 meters above sea level. If you somehow picked up Everest, flipped it upside down, and dropped it into Challenger Deep, tip first, like the world's most dramatic party trick, the summit of Everest would disappear beneath the surface and still be sitting under more than a mile of water before it touched the bottom. A mile of open ocean above the top of the tallest mountain on Earth. Let that image sit for a second. Everest, which takes the most elite climbers on the planet weeks of grueling effort and several toes worth of frostbite to summit, would be completely swallowed by this trench like it was nothing. It wouldn't even be close. This is the kind of place we're talking about, and we barely know it exists. The trench exists because of a geological process called subduction, which sounds like a Bond villain's plan but is actually just plate tectonics doing its thing. The Pacific Plate, one of the massive slabs of rock that make up Earth's outer shell, is slowly sliding underneath the Mariana Plate. Slowly here means a few centimeters per year, roughly the same speed your fingernails grow, which is either reassuring or terrifying depending on your perspective. As the denser Pacific Plate dives down into the mantle, it drags the ocean floor down with it, creating a deep trench along the boundary. This is not a passive process. The grinding, the heat, the compression, its relentless geological violence happening in extremely slow motion, and the Mariana Trench is the result. The planet folding in on itself, creating a wound that goes deeper than anything else on the surface of the Earth. Here's something that tends to surprise people. The Mariana Trench isn't the only deep ocean trench out there. The Pacific Rim is dotted with them. The Tonga Trench, the Philippine Trench, the Kuril-Kamchatka Trench. Subduction zones produce these features wherever two plates meet and one decides to go under. But the Mariana Trench is the deepest, the most studied, and in many ways the most extreme. It is the undisputed record holder, and nobody's going to be beating that record on Earth anytime soon, because the geological conditions that would need to align for something deeper simply don't exist here. Now let's talk about pressure, because depth alone doesn't tell the whole story. Water is heavy. This is obvious when you're lugging a 5-gallon jug across a parking lot, but it becomes almost abstract when you try to scale it up to oceanic levels. Every 10 meters of water depth adds roughly 1 atmosphere of pressure, meaning the force bearing down on everything increases by about 14.7 pounds per square inch for every 33 feet you descend. At the surface, you're under 1 atmosphere of pressure, which is what your body's designed for. At the deepest point of Challenger Deep, the pressure is approximately 1,086 atmospheres. That's roughly 15,900 pounds per square inch bearing down on every surface. For comparison, a standard car tyre is inflated to about 30 to 35 pounds per square inch. You're now imagining a car tyre inflated to the equivalent of 450 times its normal pressure. It would not end well for the tyre. What this pressure does to objects is genuinely spectacular, and by spectacular I mean in the way that watching a hydraulic press flatten things on the internet is spectacular. Not beautiful exactly, but you cannot look away. Wooden objects get compressed until all the air is squeezed out and they become dense, dark, unrecognizable versions of themselves. Styrofoam cups sent down with research equipment come back the size of a thumb, every air pocket crushed out of existence. Metal equipment designed for deep-sea research has to be engineered with extraordinary precision, because the difference between a structural design that works and one that fails at those depths is the difference between a successful dive and a very bad day. Submarines designed for military use typically operate at depths nowhere near Challenger Deep. A standard nuclear submarine has a crush depth somewhere around 700 to 900 meters. At the bottom of the Mariana Trench, it wouldn't last long enough to be dramatic about it. And yet life is down there. But we'll get to that. The other thing worth understanding about the Mariana Trench is the darkness. This isn't the cozy darkness of a bedroom with the lights off, or even the more serious darkness of a cave system where you can still theoretically have a torch. This is absolute, total, geological darkness. Sunlight penetrates the ocean to a maximum depth of about 200 meters under ideal conditions. Clear water directs sunlight the right angle. Below 1,000 meters, the ocean is completely, permanently, irreversibly dark. Not dim, not shadowy. Dark in a way that has never once, in the entire history of the planet, been interrupted by natural light. The bottom of the Mariana Trench has not seen a single photon of sunlight since before the dinosaurs. Possibly ever, depending on how the geometry of the trench has shifted over geological time. When the first submersibles turned their lights on down there, they were introducing something genuinely alien to that environment, the concept of visible light. Temperature down there settles into a narrow, frigid range. Near the bottom of Challenger Deep, water temperatures hover between 1 and 4 degrees Celsius, just above freezing perpetually, without variation, because the sun's warmth has no mechanism to reach that far down, and the geothermal heat from below is diffuse and gradual. There are no seasons at 11 kilometers depth. There is no weather. There are no tides of meaningful consequence. There is pressure, there is cold, there is darkness, and there is an almost meditative, unbroken stillness that has lasted millions of years. Which, for the record, sounds absolutely miserable if you're a human being, and absolutely ideal if you are a certain category of extremorphal organism that has had several 100 million years to figure out how to make it work. The water column above the Mariana Trench, the miles of ocean between the surface and the bottom, acts as a kind of filter and conveyor belt simultaneously. Organic material from the surface world, everything from dead plankton to whale carcasses to particles of food that drift down from shallower ecosystems, slowly sinks through the water column in what oceanographers call marine snow. It is a perpetual slow-motion blizzard of organic matter drifting downward in the dark. By the time it reaches the bottom, it has been transformed by pressure, by the cold, by the bacterial communities that work on it along the way. What arrives at Challenger Deep is not what fell from the surface. It is processed, altered, condensed. And it is food, the basic fuel that sustains whatever is living down there in the absence of every other energy source most of us would consider non-negotiable. The Mariana Trench, then, is not simply a deep place. It is a system, a geological, chemical, biological system operating under rules that barely resemble the ones we take for granted up here at the surface. It has its own physics, effectively, its own chemistry, its own ecology. Calling it just a trench is like calling the Amazon just a river. Technically accurate, wildly inadequate, and a little embarrassing if you know what you're actually dealing with. We spent centuries looking up at the stars and speculating about what might be out there. We built telescopes and calculated orbits and pointed satellites at distant galaxies. Meanwhile, right here on Earth, under several miles of ocean water in a trench that takes up a significant slice of the Western Pacific, there was an entirely different world sitting quietly in the dark, not asking to be discovered, not advertising itself in any way, just existing, doing whatever it is that things do when no one is watching, which as it turns out is quite a lot. Understanding the basic anatomy of this place, its scale, its pressure, its permanent darkness, its geological origins, is the first step to understanding why everything scientists eventually found there turned every assumption about life on Earth completely upside down. Because here's the spoiler nobody was expecting. The trench wasn't empty, it was packed. And what was living down there wasn't just surviving. In some cases, it was thriving. To understand just how audacious the first descent into the Mariana Trench actually was, you need to appreciate the context. It was 1960. The space race was barely off the launch pad. Yuri Gagarin wouldn't reach orbit until the following year. Commercial jet travel had just become a reality for ordinary people. The most powerful computers on the planet were the size of a living room, and roughly as capable as a modern pocket calculator. And in this technological environment, two men looked at each other, looked at the deepest, most inhospitable place on Earth and said, yes, we should go down there, in a metal ball, voluntarily. The vessel they climbed into was called the Trieste, and it deserves its own moment of appreciation, because it was simultaneously a marvel of engineering and something that looked like it had been designed by a committee that had never quite agreed on what they were building. The upper portion was a large float tank filled with aviation gasoline, lighter than water, which provided the buoyancy that kept the whole structure from simply plummeting. Attached to the bottom of this tank on a kind of frame was a steel pressure sphere roughly 2 meters in diameter. That sphere was where the crew lived for the duration of the dive, 2 meters across, smaller than most garden sheds. 2 adult human beings were going to spend the better part of a day inside this thing, descending into permanent darkness and pressure that had never been tested at full scale by anything human-made. And they were excited about it. This is either the definition of bravery or evidence that the 1960s had a fundamentally different relationship with personal risk assessment. Possibly both. The 2 men making the descent were Jacques Piccard, a Swiss oceanographer, and the son of Auguste Piccard, who had designed and built the Trieste, and Don Walsh, a lieutenant in the United States Navy. Piccard brought the scientific expertise and a deep personal connection to the vessel. This was, in a very real sense, his family's machine. Walsh brought the institutional backing of the US Navy, which had acquired the Trieste and was funding the mission. Together they were about as well prepared as any 2 humans could be for something that had absolutely never been attempted, which meant they were working largely on calculation, engineering confidence, and the kind of optimism that only exists when you haven't yet experienced the thing you're being optimistic about. They sealed the hatch on the morning of January 23, 1960, in the waters above Challenger Deep, and then they began to sink. The descent took approximately 4 hours and 48 minutes, nearly 5 hours of dropping through complete darkness, watching the pressure gauges climb steadily toward numbers that would have been theoretical nightmares for any other vehicle. Every few minutes the readings ticked upward, past the depths where military submarines operate, past the depths where any light penetrates, past every benchmark that human engineering had previously bothered to design for. The Trieste was built specifically for this, but that didn't make the gauges any less confronting to watch. The water outside the viewport was black in a way that has no real equivalent on the surface world. Not dark like a room with the curtains drawn. Dark like the concept of light had never been invented. At around 9,000 meters, something happened that would have made most people immediately request to go back up. There was a loud crack, Sharp, sudden, the kind of sound that in any normal context means something has gone structurally wrong. Pickard and Walsh looked at each other. They checked the instruments. Nothing appeared to be failing. They investigated as thoroughly as you can investigate anything from inside a 2-meter sphere, with limited ability to actually inspect the exterior. Eventually they determined that one of the plexiglass window panes in the entry tunnel, not the main viewport but a secondary piece, had cracked under the pressure. The sphere itself was intact. The critical systems were functioning. And so, in a decision that says everything you need to know about the personality types required for this kind of work, they kept going. They did not turn around. They noted it in the log and continued the descent. This is the kind of behavior that makes engineers reading mission reports physically uncomfortable. They reached the bottom at a depth later confirmed to be approximately 10,916 meters. Measurements have been refined several times since, but this was the first human contact with the floor of Challenger Deep. The Trieste settled gently onto the sediment, stirring up a cloud of pale, fine material that drifted in the beam of the exterior lights like slow-motion smoke. The floor wasn't a hard rock surface as some had imagined. It was soft. Diatomaceous ooze, essentially the compressed remnants of billions of microscopic organisms that had been raining down from the surface for millions of years, layer by layer, century by century, until they formed a thick biological carpet on the lowest floor of the ocean. Pickard and Walsh had about 20 minutes at the bottom, 20 minutes to look around, take readings, observe what they could through the small viewport. Given the years of preparation, the engineering effort, the 5-hour descent and the existential weight of the moment, 20 minutes feels almost comic, like flying to the other side of the planet for a lunch meeting and having to leave before. Dessert. But the Trieste wasn't designed for extended stays. It was designed to get there, confirm it could be done, gather what data it could and come back, which it did. But here is the part that rewrote the rulebook. While sitting on the floor of the deepest place on Earth, a place where the pressure was over 1,000 times what you experienced standing at sea level, where no sunlight had ever reached, where temperatures were barely above freezing, where every established model of survivable biology suggested nothing complex should be able to exist. Pickard looked out the viewport and saw a fish. Not bacteria, not something microscopic, a fish. A flat, pale creature moving slowly along the bottom, apparently completely unbothered by conditions that should have been, according to every model biologist had at the time, completely lethal to anything with a nervous system. It looked like a type of flounder, though there is some scientific debate about this identification, partly because the observation was brief and the conditions for photography were not ideal, and partly because everyone involved was probably still processing the emotional aftermath of spending 5 hours falling through the dark in a metal ball. What is not debatable is that something living was down there, something with a backbone, something that had evolved not merely to survive those conditions but apparently to navigate them with complete composure. This observation, one man looking through a small porthole at the bottom of the world, watching a fish go about its day, demolished one of the foundational assumptions of 20th century marine biology. The deep ocean, particularly at Hadal depths below 6,000 meters, had been classified in the scientific imagination as essentially sterile, a chemical environment. Rocks and pressure and cold, and perhaps some bacteria clinging to surfaces, but nothing that you would recognize as an animal. The idea that vertebrates, animals with complex physiology, organ systems, nervous systems, the whole biological package, could not only survive but apparently live at those depths, had been considered effectively impossible. And then 2 men in a metal sphere sat on the bottom and watched one swimming past. The scientific community's reaction was, predictably, complicated. Some researchers were electrified by the implication, if fish could live there, what else could? Others were more cautious, noting the brevity of the observation and questioning the identification. But the question had been permanently and irrevocably opened. Whatever was or wasn't at the bottom of Challenger Deep, the old answer, nothing basically, was no longer available as a default position. The trench would have to be investigated more seriously. And when better cameras and unmanned probes eventually made the journey, what they found validated the moment completely, and then raised the stakes considerably higher. For most of the 20th century, the scientific consensus on deep ocean life went roughly like this. Shallow water, lots of life. Medium depth, some life. Very deep, less life. Hadal depths, below 6,000 meters, essentially nothing worth writing home about. This wasn't an unreasonable position given what was known at the time. Biology runs on energy. Energy in the ocean comes from the sun. Sunlight stops at around 200 meters. Below that, organisms have to survive on whatever scraps drift down from the sunlit zones above, and the deeper you go, the fewer scraps arrive, because everything edible gets eaten on the way down. By the time you reach 10,000 meters, the logic ran, there shouldn't be enough energy input to sustain anything more complex than the occasional hardy microbe. It was a clean, logical, well-reasoned conclusion. It was also wrong in ways that nobody fully appreciated until cameras started going down and coming back, with footage that made biologists question everything they thought they knew about the rules of life. The first wave of unmanned probe deployments into deep ocean trenches through the 1970s and 1980s began returning images that did not match the expected sterile emptiness. There were creatures down there, not traces, not chemical signatures. Actual animals, moving, feeding, apparently thriving in conditions that should have ruled them out entirely. And the more researchers looked, the more they found, and the stranger it got. Take the Hadal amphipods. These are small crustaceans distantly related to the shrimp you might find in a seafood dish, and they are absolutely everywhere in the deep trenches. Not scattered occasionally, swarming. Researchers who sent down lander traps baited with food were retrieving them packed with thousands of amphipods within hours, at depths exceeding 10,000 meters, in crushing pressure, near freezing temperatures, and total darkness. The amphipods were not struggling. They were competing aggressively for food, crawling over each other, entirely at home. For an organism roughly a centimetre long, this level of abundance at those depths was staggering. One study retrieved a single lander trap from Challenger Deep and found over 6,000 individual amphipods inside it. 6,000. In a trap that had been sitting on the bottom for a matter of hours. The abyss, it turned out, was not quiet. It was teeming. But amphipods were just the beginning of the inventory. Cameras and remotely operated vehicles gradually revealed an ecosystem of extraordinary and deeply unsettling diversity. Sea cucumbers, long-bodied and translucent, moved across the sediment floor in drifting herds, and herds is genuinely the right word, because researchers observed them in groups of hundreds, processing the soft sediment like slow, gelatinous vacuum cleaners. Polychaete worms writhed through the ooze. Holothurians, another class of sea cucumber relatives, were found at depths no one had thought possible for animals with their physiology. Foraminifera, single-celled organisms that build shells, were discovered forming giant aggregates visible to the naked eye, which shouldn't be possible for single-celled organisms by any prior understanding of the scale at which such creatures operate. What made all of this biologically fascinating, and slightly alarming if you're the kind of person who finds comfort in established scientific frameworks, was not just the presence of these organisms, but the specific adaptations they had developed to function in those conditions. Animals at extreme depth face a problem that surface animals don't. The pressure at those depths affects the very molecules that make biology work. Proteins, which are the engines of every cellular process, fold into specific three-dimensional shapes to function. Pressure disrupts that folding. At 1,000 atmospheres, most proteins from surface organisms would be pushed into shapes that don't work, effectively switching off every biological process simultaneously. This is why a human being can't simply dive to 10,000 meters and expect to survive. It's not just the structural crushing pressure that would kill you, it's the fact that your cellular machinery would stop functioning at the molecular level well. Before that, deep-sea organisms have evolved a remarkable biochemical solution to this problem. Their proteins are structurally different, built with modifications that keep them stable and functional under extreme pressure. The amino acid sequences are adjusted at key positions to prevent pressure-induced misfolding. Some species also accumulate a molecule called trimethylamine oxide, or TMAO, in their tissues. TMAO acts as a kind of molecular buffer, counteracting the compressive effects of pressure on protein structure. Fascinatingly, researchers have found that the concentration of TMAO in fish tissue scales almost perfectly with the depth at which the fish lives. The deeper the fish, the more TMAO it carries. It's a biological pressure compensation system refined over millions of years of evolution, and it is elegant in a way that genuinely makes you appreciate how good life is at solving problems when given enough time. Current evidence suggests that for fish with this system, the functional depth limit is around 8,000 to 8,500 meters. Beyond that, even TMAO-enhanced proteins can't fully compensate, which may explain why fish haven't been conclusively documented. Below that depth, even in trenches that go deeper. This is the kind of detail that sounds like a footnote but is actually profound. Life didn't just accidentally wander into the deep ocean and tough it out. It evolved dedicated molecular technology to make those conditions workable. That's not survival. That's optimization. The visual appearance of deep Hadal life is something else worth pausing on, because it is genuinely spectacular in the most alien way possible. Most deep-sea creatures found in the trench zones are pale to the point of translucency, white, cream, or ghostly pink, with skin through which internal organs are sometimes partially visible. Colour is metabolically expensive to produce, and in an environment where no light reaches, there is no evolutionary reason to bother. The result is a population of creatures that look like they've been dipped in milk, moving through the dark with a kind of eerie, drifting elegance. Some of the larger amphipods seen on camera in their native environment have a quality that's difficult to describe. They look both completely biological and somehow unreal, like props from a film set that were never meant to be examined too closely. The snailfish, a family of elongated, soft-bodied fish, turned out to be among the deepest living vertebrates on record, with individuals documented at depths approaching and potentially exceeding 8,000 meters in various trenches. They are not impressive-looking animals by the standards of surface marine life. Pale, slightly saggy in appearance, with a broad flattened head and a body that tapers into a long thin tail, they look like someone sketched a fish from memory in low light. But their biochemistry is extraordinary. Their pressure adaptations are among the most sophisticated documented invertebrates, and they exist at depths that should, by all prior logic, be completely off the table for creatures of their complexity. The fact that they not only exist there but appear to be active predators, hunting and feeding successfully in pitch blackness at pressures that would crumple a car, is one of the most striking demonstrations of what evolution can accomplish given sufficient time and motivation. What was emerging from all of this research was a picture that overturned the foundational assumption that deep trenches were biological dead zones. They weren't dead. They were different, operating on different energy inputs, organized around different ecological principles, populated by creatures built to different specifications. The trench wasn't a place where life had given up. It was a place where life had gone in a completely different direction, quietly, over millions of years, without telling anyone on the surface what it was up to. And the surface, for its part, had assumed the silence meant nothing was happening. Turns out the silence just meant nobody was listening closely enough. Every expedition that has gone down since has added to the inventory. New species are discovered on essentially every serious deep trench research mission. The picture isn't getting simpler as we learn more. It's getting more complex, more layered, more densely populated than the original sterile void hypothesis would have considered remotely plausible. And the deeper the research tools can go, the more extraordinary the findings become. The abyss, it turned out, had been busy the entire time. It just didn't need anyone to know about it. Here is something that almost nobody stops to think about. Every single thing you have ever eaten traces its energy back to the sun. Every salad, every steak, every piece of bread, every cup of coffee, at some point in its chain of origin, a plant absorbed sunlight and converted it into chemical energy, and everything else built on top of that. Cows eat grass. Grass eats sunlight. You eat the cow. The sun is the silent, invisible ingredient in literally every meal in human history. We built entire religions around it. Ancient civilizations tracked its movements with extraordinary precision. We named a day of the week after it. This felt reasonable, because the sun wasn't just important. It was the only game in town. The foundational premise of all surface life, so obvious it barely needed to be stated, was that without sunlight the food chain collapses. No sun, no plants. No plants, no animals. No animals, no ecosystems. Simple, logical, universal. Except it isn't universal. Not even close. And we found that out in 1977 in one of the most genuinely disorienting scientific discoveries of the 20th century, which is saying something given the competition. The discovery happened not in the Mariana Trench specifically, but in the deep Pacific Ocean near the Galapagos Islands, where a research team was surveying the ocean floor using an early remotely operated camera system. They were looking for hydrothermal vents, fissures in the seafloor where geothermally heated water gets pushed back up through the crust. These had been theorized to exist but never directly observed. What the researchers expected to find around these vents, if they found them, was essentially nothing. Hot water and rocks, maybe some mineral deposits. The deep ocean floor in that era was still filed under empty, because the logic of photosynthesis-dependent life made everything else seem implausible. What the cameras actually found was so unexpected that the researchers on the surface ship reportedly stopped mid-conversation to stare at the monitor in silence. Around these vents was a full, dense, thriving ecosystem unlike anything that had been documented before. Giant tube worms in clusters, mats of bacteria coating every surface. Crabs, shrimp, clams, all living in apparent abundance, all organized around the vent like it was the center of their world. Which, it turned out, it was. This wasn't a few opportunistic creatures that had wandered past. This was a complete ecological community, self-contained and self-sustaining, operating in total darkness, at depths where photosynthesis was physically impossible, miles from the nearest sunlit water. The team reportedly broke out a bottle of champagne that had been stored on the ship for a special occasion. This qualified. Understanding what was actually happening required working out the biochemistry from scratch, because nothing in the existing framework of marine biology quite explained it. The answer, when it emerged, was chemosynthesis, a process that uses chemical reactions rather than light as the primary energy source for building organic matter. Hydrothermal vents pump out superheated water loaded with hydrogen sulfide, methane, and other reduced chemical compounds. Certain bacteria and archaea, the true founding organisms of these ecosystems, have evolved the metabolic machinery to oxidize these compounds and use the energy released to fix carbon dioxide into organic molecules. Exactly what photosynthesis does with light energy, but running entirely on chemistry. No photons required, no sun. Just rocks and heat and the right microbes with the right enzymes, quietly converting geothermal energy into the biological currency that everything else in the ecosystem runs on. This was not a minor footnote. This was the discovery that Earth had been running two completely separate operating systems for life all along, and we had only ever booted up one of them. The photosynthesis-based system that powers the surface world is the one we know, the one we study, the one that fills every ecology textbook. The chemosynthesis-based system at hydrothermal vents had been running in parallel in the dark for billions of years, and nobody on the surface had the slightest idea. Not because it was hidden, exactly, but because the tools and the conceptual framework to find it hadn't existed yet. It was the biological equivalent of living in a house for your entire life, and then one day discovering a fully furnished basement you never knew was there. Now, the tube worms. Because we need to talk about the tube worms, and honestly, once you hear about them, you will probably bring them up in conversation more than is socially expected of you. Giant tube worms, Riftia pachyptila, for those keeping track of Latin names, are the flagship organism of deep-sea hydrothermal vent ecosystems, and they are extraordinary in ways that escalate with every detail. They can grow to over 2 meters in length, which means they are roughly the size of a tall adult human, except cylindrical, bright red at the top where a feathery plume emerges from the tube, and completely without a conventional digestive system. No mouth, no stomach, no intestines, not vestigial ones, not reduced ones, none, zero. They are, from a conventional biological standpoint, not set up to eat in any recognizable way, which makes their existence as large, thriving organisms in a nutrient-depleted environment seem like a fairly fundamental contradiction. The solution life came up with is, depending on your perspective, either brilliant or deeply unsettling. The interior of a giant tube worm is packed with a specialized organ called the trophosome, which contains billions, and that is not an exaggeration, billions of chemosynthetic bacteria living inside the worm's tissue. The worm provides the bacteria with hydrogen sulfide and oxygen, transported through the blood via a specialized hemoglobin molecule that can carry both simultaneously without them reacting with each other, which is a biochemical trick that took researchers considerable time to figure out. The bacteria convert those compounds through chemosynthesis and produce organic molecules, which the worm then absorbs directly from its own internal bacterial population. The worm doesn't eat. The worm is essentially a mobile housing unit for a bacterial colony, and the colony pays its rent in calories. It is the world's most extreme roommate arrangement, refined over millions of years of evolution into something that works with remarkable efficiency. The hemoglobin in tube worms deserves its own mention, because it is chemically unusual in a way that highlights exactly how far evolution will go when it has time and necessity on its side. Hydrogen sulfide, the compound the bacteria need, is toxic to virtually all animals. It's the chemical responsible for the smell of rotten eggs, and at even modest concentrations it shuts down mitochondrial function in most organisms. Tube worms live immersed in it. Their blood contains a modified hemoglobin that binds hydrogen sulfide without being poisoned by it, and transports it safely to the bacteria inside the trophosome. This protein didn't exist in any known organism before tube worms were discovered. It was invented, in the evolutionary sense of the word, specifically to solve the problem of living productively next to a hydrothermal vent. Biology once again doing something that seemed impossible right up until the moment you found out it was already being done. The ecosystem around hydrothermal vents isn't limited to tube worms and bacteria, though they are the most visually dramatic components. Vent clams have evolved similar symbiotic relationships with chemosynthetic bacteria, carrying them in their gill tissue. Vent shrimp cluster in enormous numbers around vents on the mid-Atlantic ridge, equipped with a highly modified organ on their backs that appears to be light-sensitive, possibly detecting the faint infrared glow of the hot water, which suggests a kind of vision adapted to perceive geothermal energy rather than solar light, which is the kind of evolutionary development that sounds like science fiction, until you remember that the ocean has had several 100 million years to workshop these ideas. Vent crabs patrol the perimeter, predatory fish hover at the edges, full trophic levels from primary producers to apex predators, all running on chemical energy from the Earth's interior. A complete world sealed off from the sun entirely, and apparently doing quite well without it. What makes chemosynthesis philosophically staggering, beyond just the biological mechanics, is what it says about the fundamental requirements for life. For most of human intellectual history, and right up until 1977, the working assumption was that life needed certain things: liquid water, an energy source, organic chemistry, and the right temperature range. The sun provided the energy in every example we had. That seemed like a fixed requirement. Chemosynthesis removed it from the list. Suddenly, life only needed liquid water, chemical energy gradients, and the right molecular ingredients. And chemical energy gradients don't require a star. They require geology. They require heat differentials and mineral-rich water, and the basic physics of planetary interiors. Which means life as a phenomenon is potentially far more widespread in the universe than anyone had seriously considered before 1977, because those conditions exist in a lot of places. A lot of cold, dark, seemingly barren places that used to be filed under definitely no life here, and now have to be reclassified as possibly worth checking. This is the part where the Mariana Trench stops being just an ocean feature and starts being a window into something much larger. The biology down there isn't just unusual. It isn't just a curiosity for marine biologists to argue about at conferences. It is, in a very direct and concrete way, a proof of concept for life in the universe. Every chemosynthetic organism thriving in the permanent darkness of the deep ocean is a data point in the argument that life doesn't need the things we assumed it needed. It just needs chemistry. And chemistry, as it turns out, is everywhere. The universe is absolutely full of it, which means the basement we found in our own house might be a very common feature of houses in general, and we've barely started knocking on doors. The tube worms, meanwhile, continue to grow in the dark at hydrothermal vents across the ocean floor, entirely unaware of the philosophical implications they carry. They are not impressed with themselves. They are just doing what evolution figured out millions of years ago, converting poison into calories, carrying their bacteria with them wherever they go, growing 2 meters long without ever once needing a stomach. Quietly extraordinary in the absolute darkness, at the bottom of a world most people have never thought about twice. There is a popular idea in modern productivity culture that stress makes you sharper. Pressure creates diamonds. Adversity breeds resilience. Disruption forces innovation. This framework is everywhere. In business books, in motivational speeches, in the biographies of people who survived something terrible and then built a company. The implicit assumption is that change is the engine of improvement, and that stability, comfort, and predictability are the enemies of growth. Environments that stay the same produce organisms, or people, or institutions that stay the same. Stagnation, in this view, is just another word for slow death. The deep ocean would like a word. Because what has happened in the stable, cold, pressurized darkness of the Hadal zone over the past several 100 million years is not stagnation. It is, in many ways, the most sophisticated and refined biological engineering on the planet, and it happened not because of constant disruption and change, but precisely because of the absence of it. The deep ocean trenches are among the most stable environments on Earth. The temperature doesn't vary meaningfully. There are no seasons. There are no storms, no droughts, no glaciers advancing and retreating, no asteroid impacts directly rearranging the local neighborhood. The pressure is constant. The darkness is absolute and permanent. The chemical composition of the water changes on geological rather than seasonal timescales. By the standards of surface environments, the deep ocean is essentially frozen in place, and that frozen-in-place quality, it turns out, is not a limitation. It is a laboratory condition, one that has been running continuously for longer than most surface ecosystems have existed in their current form. To understand why stability accelerates certain kinds of evolution rather than halting it, you need to think about what disruption actually does to an evolutionary process. Surface ecosystems are constantly being reset. A volcanic eruption wipes out a local population. A climate shift changes which species can survive in a given region. A new predator arrives and reshuffles the food chain. An ice age pushes entire ecosystems toward the equator and pulls them back when the ice retreats. Every time something like this happens, the organisms in that ecosystem face a new set of pressures, and natural selection responds by favoring whatever traits happen to be useful in the new situation, not the optimal traits in any absolute sense, but the best available traits given current conditions and current gene pools. Surface evolution is, in a sense, always playing catch-up. It's constantly being interrupted mid-sentence, forced to start a new paragraph before the previous thought was finished. Deep ocean evolution has no such interruptions. The sentence keeps going. For millions of years, the selection pressures in the Hadal zone have remained essentially consistent. Survive the pressure, manage the cold, find food in the dark, avoid being eaten, reproduce. That's it. No sudden new variables, no resets, no forced pivots. And when a consistent selection pressure operates on a population for long enough without interruption, something remarkable happens. The solutions stop being good enough for current conditions and start becoming genuinely optimal. The proteins become more efficiently folded for exactly the pressure they experience. The metabolic pathways become more precisely calibrated for the exact chemical environment. The sensory systems become extraordinarily attuned to the specific signals available. Pressure gradients, chemical traces, the faintest mechanical vibrations in the water. Everything about these organisms is finely tuned in a way that surface organisms simply don't need to be, because surface organisms are always one environmental disruption away from those carefully optimized traits becoming irrelevant. Think of it like this. Imagine two engineers working on the same problem. The first engineer gets a clear brief, a long timeline, and no interruptions. They can iterate slowly and carefully, test each modification, discard what doesn't work, refine what does, and keep improving without ever having to throw out their work and start over. The second engineer works in an open-plan office where someone changes the project requirements every 3 months. The software platform they're using gets updated twice a year, and occasionally the entire building has to be evacuated because of a fire drill. The second engineer will probably come up with something functional. The first engineer, given enough time, will come up with something extraordinary. Deep ocean organisms are the first engineer. They have had geological timescales with no fire drills, no platform updates, and no one changing the brief. The Hadal amphipods mentioned earlier are a good case study in what long-term stable optimization actually looks like in practice. These small crustaceans have had tens of millions of years of uninterrupted selection for exactly one environment. The result is an organism whose biochemistry is calibrated so precisely for its specific depth range that transplanting it to shallower water doesn't save it, it kills it. The pressure adaptations aren't general-purpose deep-sea modifications. They are tuned to specific pressure ranges, specific temperature windows, specific chemical conditions. There's no flexibility built in because flexibility costs energy and has never been necessary. These are organisms that have been so thoroughly optimized for one particular set of conditions that they are, effectively, the world's most specialized professional, extraordinary at their job, useless at everything else. Which, from an evolutionary standpoint, is exactly the right outcome when your environment is going to stay the same for the next 50 million years. The enzymatic systems of deep-sea organisms show the same pattern. Enzymes, the molecular machines that catalyze every biological reaction, have optimal operating ranges. Temperature affects their function significantly, which is why your body maintains a very precise core temperature, and why a fever, even a modest one, can disrupt your biology enough to make you feel terrible. Surface organisms generally carry enzymes calibrated for a range of temperatures because surface temperatures vary. Deep-sea organisms carry enzymes calibrated with extraordinary precision for the exact temperature at their depth. Cold-adapted enzymes in hadal organisms have structural modifications that keep them flexible and functional at near-freezing temperatures, where the equivalent enzyme from a surface organism would become too rigid to work properly. But those same cold-adapted enzymes would fall apart at surface temperatures. They're too loose, too flexible for warmer conditions. Perfect for one thing, nothing else. Long-term optimization at its most extreme. There's another dimension to deep-sea stability that deserves attention, which is what it does to genetic diversity and speciation over time. In surface ecosystems, populations get fragmented by geography, mountain ranges, rivers, climate zones, and those fragmented populations diverge genetically over time, eventually becoming separate species. The deep ocean trenches are isolated from each other by mid-ocean ridges and other geological features, which means the populations in the Mariana Trench have been largely separated from populations in other trenches for millions of years. And with no dramatic climate events forcing migrations or mixing, those populations have been quietly diverging in their own directions. The result is that deep ocean trenches have remarkably high levels of endemic species, organisms found nowhere else on Earth, and the genetic distance between populations in different trenches, even for superficially similar-looking organisms, can be astonishing. The same type of amphipod found in different trenches often turns out to be genetically so distinct that calling them the same species is a stretch. They look similar because they face similar pressures. But inside, at the molecular level, they've been running separate evolutionary experiments for so long that the differences are profound. There is something almost meditative about this, if you sit with it long enough. While the surface world was cycling through ice ages and mass extinctions and continental rearrangements, while dinosaurs rose and fell and mammals took over, and primates developed the cognitive complexity to eventually build submarines and point. Cameras at the deep ocean floor, through all of that, the organisms in the trenches were just quietly working on the same problem. No drama, no pivots, no pivot to video, no disruptive rebranding, no paradigm shifts. Just the slow, patient, uninterrupted work of becoming better at exactly one thing, over a time span that makes the entire history of human civilization look like a rounding error. The irony, of course, is that the extreme specialization that makes deep-sea organisms so fascinating and so scientifically valuable also makes them extraordinarily vulnerable to the one kind of disruption they've never had to deal with: the surface. World arriving at their door. Deep-sea mining operations, which have been proposed and in some cases begun in various locations, threaten to physically destroy habitats that have been stable for geological ages. Organisms that have spent millions of years optimizing for a specific environment have no evolutionary toolkit for rapid adaptation. They can't pivot. They can't adjust. The flexibility that surface organisms have because of their history of dealing with change simply doesn't exist in an organism that has never needed it. This isn't a weakness in any meaningful evolutionary sense. It's the logical consequence of a strategy that worked perfectly for hundreds of millions of years. It only becomes a problem when something from outside the system shows up and starts rearranging things at a pace that evolution cannot possibly match. The deep ocean trenches are, in this sense, a portrait of what life can become when given enough time and enough quiet. Not explosive, diverse, constantly adapting life in the surface mold, but refined, precise, deeply specialized life that has worked out the optimal solution to a fixed problem and then kept polishing it for longer than most surface ecosystems have. Existed. It is evolution running in a different mode entirely. Less jazz improvisation, more classical composition, Long, slow, deliberate, and by the time you finally hear the finished piece, extraordinary in ways that quick work rarely achieves. Let's talk about what it means to be old. Not needs reading glasses old, not remembers when gas was cheap old. Really, cosmically, almost incomprehensibly old. Because buried in the sediment layers at the bottom of Challenger Deep, in the soft, fine ooze that Piccard and Walsh disturbed with their landing back in 1960, researchers have found microbial communities that may have been living continuously for hundreds of millions of years. Not descendants of ancient organisms, not organisms that look like ancient ones. The same communities, or something extraordinarily close to them, persisting in an unbroken biological thread that stretches back to a time when the planet was so different it would be unrecognizable. To put that in perspective, the dinosaurs showed up roughly 230 million years ago and went extinct about 66 million years ago. Some of the microbial communities found in deep ocean sediments appear to have been active, quietly, slowly, almost imperceptibly active, across that entire window and well beyond it. These microbes were here before the first dinosaur hatched from its egg. They were here while every major lineage of dinosaur rose and diversified and ruled the planet, and they were here when the asteroid hit and ended the whole show. They didn't notice, or if they did, nothing in their behavior reflected it. They just kept doing what they do at their extraordinarily unhurried pace, in the cold and the dark and the silence. The pace is worth pausing on, because it is one of the most disorienting facts in all of deep-sea microbiology. These organisms reproduce so slowly that a single generation, the time from parent cell to daughter cell, can span decades. Decades. Organisms at the surface, even long-lived ones, reproduce on timescales of hours to years. Bacteria in your gut can complete a full generation in 20 minutes. The microbes in Challenger Deep sediment operate on a timescale that makes a human lifetime look like a busy Tuesday. Researchers studying sediment cores from deep ocean trenches have calculated metabolic rates so low that the organisms are essentially operating at the minimum theoretical threshold for being technically alive, consuming just enough energy to maintain their cellular structure without falling apart, dividing just often enough to qualify as a reproducing population. They are life-running on the absolute lowest possible setting, not dying, not thriving in any way a surface biologist would recognize, just persisting, with a patience that has no surface equivalent and probably shouldn't. What actually enabled the discovery of these communities was the sediment itself. The ocean floor accumulates material over geological time, the constant downward drift of organic particles, mineral dust blown from continents, the shells of surface organisms that die and sink. This accumulation is slow, typically a few millimeters per thousand years in deep trenches, which means a sediment core drilled from the bottom of Challenger Deep is essentially a time capsule with layers corresponding to different geological eras. The top centimeters represent recent times. Deeper down, you're sampling material from tens of millions of years ago. Researchers who extracted long sediment cores from Hadal zones and then cultured the microbes from different depth layers found something startling. The microbes were still alive in layers corresponding to sediment deposited over 100 million years ago. Not fossilized, not dormant in any conventional spore-forming sense. Metabolically active, detectable by the gases they produced, responding to added nutrients when researchers provided them in laboratory conditions. Old microbes on fresh food, after an unimaginable wait, and still willing to eat. The survival mechanism here isn't some dramatic biological trick. It's more like the microbial equivalent of extreme frugality. In environments with essentially no energy input, the deep sediment receives virtually none of the organic material that rains down to the immediate surface of the trench floor, because it gets consumed by the organisms living above, the microbes, have evolved to run their cellular machinery at such low power that their energy requirements become almost fictional. Some researchers have described it as existing in a state between life and death that doesn't have a conventional biological category. They are too alive to be called dormant and too slow to be called active in any meaningful surface biology sense. They occupy a metabolic tier that we didn't know existed before we found them, which is something that happens with inconvenient frequency when you start seriously investigating the deep ocean. Now here is where it gets genuinely philosophical, and also where the phrase living archive stops being a metaphor and starts being almost literally accurate. The genetic material in these ancient microbial communities represents an unbroken line of biological information extending back to the early history of complex life on Earth. Every generation, information gets passed on. Mutations accumulate slowly, far more slowly than in faster reproducing organisms, because fewer replications mean fewer opportunities for copying errors. The result is a genome that has changed relatively little over vast stretches of geological time. These organisms are not the same as their ancestors of 200 million years ago, in the same way that no reproducing lineage is ever identical to its deep ancestors. But they are closer to those ancient forms than almost anything else alive on Earth. Today, they are carrying molecular information in their enzymes and structural proteins and metabolic systems that has been continuously preserved through geological events that wiped out the majority of multicellular life on the planet multiple times. Consider the 5 mass extinctions in Earth's history, the large-scale die-offs that cleared out vast portions of the biosphere and reset the ecological stage for whoever was left standing. The Permian event, roughly 252 million years ago, killed an estimated 90 to 96% of all marine species and around 70% of land vertebrate species. Not 90% of individuals, 90% of species. The End Cretaceous event 66 million years ago, which finished off the non-avian dinosaurs, was actually a smaller extinction in percentage terms, though considerably more dramatic in narrative terms because it had better marketing. Through all of these events, the deep sediment microbes persisted. The asteroid impact that ended the Cretaceous sent enormous amounts of debris into the atmosphere, blocked sunlight for years, collapsed the photosynthesis-dependent food chains that everything large and impressive was running on. Down in the sediment at the bottom of the trench, the microbes that didn't run on photosynthesis, that didn't depend on surface productivity, that had been operating on geological timescales long before the asteroid had the audacity to show up, they essentially didn't register the event. The catastrophe that rearranged the surface world entirely was, from their perspective, a blip. A brief fluctuation in the slow rain of organic material from above. Nothing worth changing your schedule for. This is, depending on how you look at it, either deeply reassuring or profoundly humbling. Reassuring because it suggests that life, at its most fundamental microbial level, is nearly impossible to fully extinguish. The deep sediment communities function as a kind of biological backup system, a living repository of ancient genetic and metabolic information that mass extinctions can't reach. Whatever catastrophe hits the surface, whatever complex ecosystems collapse, whatever dominant lineages get wiped out, the microbes in the trench sediment continue to run their quiet, unhurried processes, holding genetic information that predates the catastrophe by hundreds of millions of years. Life has a deep storage drive, and it's been quietly running in the dark at the bottom of the Pacific. The humbling version of this story is the one where you realize what these organisms have witnessed in geological, if not experiential terms. Continental drift has rearranged the surface of the planet multiple times during their tenure. The supercontinent Pangaea assembled and broke apart. The Atlantic Ocean opened. The Himalayas rose. Flowering plants evolved and took over the land. Fish crawled out onto shore, and some of those descendants eventually developed the cognitive capacity to build submersibles and discover their ancient roommates in the sediment. The microbes, throughout all of this, were down there, dividing once every few decades, metabolizing at rates so low they barely register on instruments, maintaining their cellular structure through chemistry that has barely changed since before the dinosaurs were a concept. They have no awareness of any of this, obviously. They have no awareness of anything. But the information they carry in their genomes has travelled through all of those geological epochs, preserved in the stable, cold, pressurized darkness of the deep trench sediment, and it is now being read by the distant descendants of the organisms that evolved on the surface and eventually got curious enough to go looking. The scientific implications of this are considerable and still being worked out. Deep sediment microbial communities represent a source of ancient biochemical diversity, enzymes, metabolic pathways, structural proteins, that predates and has no equivalent in surface biology. Some of these ancient metabolic systems may have applications in biotechnology, medicine, or material science that researchers haven't yet begun to fully explore. More fundamentally, studying these organisms offers a direct biological window into what early Earth life looked like and how it operated. a question that surface biology can only approach through fossil records and molecular clock estimates. The microbes in the sediment aren't fossils, they're the real thing, or close enough to it that the distinction barely matters for research purposes. There is also the question of what the existence of these communities tells us about the minimum requirements for life to persist over geological timescales. The answer appears to be remarkably little: a stable, cold temperature, a small, consistent source of chemical energy, no catastrophic disturbances. Given those conditions, life can apparently continue for longer than most surface ecosystems have existed, in populations so sparse and slow-moving that they would be invisible to any casual survey. The deep sediment is life running on emergency power, indefinitely. Not thriving, not dying, just continuing, as it has been continuing since before anything we would recognize as complex biology had yet evolved on the surface above. Which, if you think about it, means that somewhere beneath our feet right now, beneath miles of ocean water and meters of accumulated sediment, there are living organisms carrying genetic memories of a world that predates every animal, every plant, every ecosystem we have ever classified. They don't know we're here. They don't know anything. But they are, in the most literal possible sense, the oldest living things on the planet. And the fact that we found them at all is one of the more extraordinary accidents in the history of science. Here is a question that almost nobody thinks to ask. If the deep ocean is so isolated, so cut off from the surface world, so thoroughly its own self-contained system, why does it matter what happens down there? If the organisms in the Mariana Trench disappeared tomorrow, would anyone on the surface notice? The answer, unfortunately for anyone hoping for a simple and comfortable response, is yes. Profoundly. And the mechanism by which a collection of pale, pressure-adapted creatures living in permanent darkness at the bottom of the Pacific Ocean actively shapes the atmosphere you are currently breathing is one of the most underappreciated stories in all of Earth science. It starts with carbon. Carbon is the fundamental currency of biology, the backbone of every organic molecule, the element around which all known life is constructed. It cycles through the Earth's systems continuously, moving between the atmosphere, the ocean, the land, and living organisms in a process that has been running since the planet first developed something resembling a biosphere. The atmospheric piece of this cycle is the one currently causing everyone considerable anxiety, for reasons that don't need extensive introduction. Carbon dioxide in the atmosphere traps heat. More CO2 means more trapped heat means a warming planet. The amount of carbon dioxide in the atmosphere at any given time is a function of how much is being added, through volcanic activity, decomposition, combustion, respiration, and how much is being removed and stored elsewhere. The deep ocean, it turns out, is doing a significant portion of the storing, more than most people realize, more than was fully appreciated until relatively recently. The mechanism is called the biological carbon pump, which sounds like something that belongs in a sci-fi novel, but is actually just a description of a natural process that has been operating for hundreds of millions of years. Here is how it works. At the ocean's surface, phytoplankton, the microscopic photosynthesizing organisms, absorb carbon dioxide from the atmosphere and convert it into organic matter. They grow, they reproduce, they get eaten by zooplankton, which get eaten by fish, which get eaten by larger fish, and so on up the food chain. But not all of that organic carbon stays in the upper ocean. A significant fraction of it, dead organisms, fecal material, shed body parts, the slow drift of biological debris, detaches from the surface food web and begins to sink. This is the marine snow we mentioned earlier, and it is the delivery system for the biological carbon pump. Every particle of organic carbon that sinks out of the surface layer and into deep water is a molecule of CO2 that has been pulled from the atmosphere and is now heading somewhere less climatically consequential. In the middle depths of the ocean, much of this sinking material gets intercepted and decomposed by bacteria, releasing the carbon back as dissolved CO2 into the water, which is not great but at least keeps it out of the atmosphere for as long as that water stays deep, which can be centuries. But the fraction that makes it all the way down to the Hadal zone, to the floor of the Mariana Trench and other deep trenches, enters a different accounting category entirely. Down there, the organisms that decompose organic matter are working in conditions where carbon, once locked into the sediment, can remain locked for thousands to millions of years. The pressure, the cold, the absence of the oxygen-rich turbulence that drives rapid decomposition in shallower water, All of it conspires to slow the process of carbon release to a near halt. Organic carbon that reaches the trench floor gets buried in the accumulating sediment, layer by layer, and effectively removed from the active carbon cycle on human-relevant timescales. The deep trenches are, in this sense, functioning as long-term carbon burial sites, geological savings accounts where carbon gets deposited and very rarely withdrawn. And the organisms living in those trenches are not passive bystanders in this process. They are the processing system. The hadal amphipods, the sea cucumbers, the bacteria, the microbial communities in the sediment, all of them are actively breaking down and transforming the organic material that arrives from above, incorporating some of it into their own biomass, mineralizing some of it into forms that lock more stably into sediment, and generally running a biological conversion process that determines how much carbon gets permanently buried versus how much eventually finds its way back toward the surface. Remove those organisms and you change the efficiency of the burial process. Change the efficiency of the burial process, and you change how much carbon the ocean pulls out of the active cycle. Change that and you have a direct line to atmospheric CO2 concentrations and ultimately to climate. The numbers involved in marine carbon cycling are large enough to make individual human contributions look modest by comparison, which is saying something. The ocean as a whole absorbs roughly a quarter to a third of the CO2 that human activity adds to the atmosphere each year. This is well established, and it is the reason that ocean acidification is a problem, because all that absorbed CO2 reacts with seawater to form carbonic acid. The biological pump contributes to a significant fraction of the ocean's long-term carbon storage capacity, beyond the simpler physical dissolution of CO2 in cold water. Estimates vary, but the biological pump is thought to be responsible for maintaining atmospheric CO, 2 concentrations tens to hundreds of parts per million lower than they would be if the ocean were biologically inert. To put that in context, the difference between pre-industrial atmospheric CO2 of around 280 parts per million and the current level of over 420 parts per million is causing the climate disruptions that are currently dominating headlines. The biological pump's contribution, the difference between a biologically active deep ocean and an inert one, is in the same order of magnitude. It is not a marginal effect, it is a foundational one. This creates a somewhat uncomfortable realization about deep-sea mining, which is the practice of extracting mineral-rich nodules and crusts from the ocean floor. These nodules, which form over millions of years as minerals precipitate out of seawater around a small nucleus, a shark tooth, a fragment of bone, whatever was lying around, contain copper, cobalt, nickel, and manganese in concentrations that are attractive to the mining industry, particularly as demand for battery metals increases with the transition to electric vehicles. The nodules are most concentrated in the abyssal plains around deep trenches, and the mining process involves essentially vacuuming the top layer of the seafloor and running it through processing equipment on a surface ship, returning the waste material as a slurry that spreads through the water column. This is, to put it diplomatically, not a gentle process. It destroys the immediate seafloor habitat completely. It creates sediment plumes that can drift for hundreds of kilometers, affecting organisms in areas far beyond the immediate mining footprint, and it disrupts the biological communities that are doing the processing work in the carbon burial system. The frustrating complexity here is that those mineral nodules are themselves part of the carbon story. They form over the same sediment layers that are doing the long-term carbon burial, and disturbing them disturbs the sediment. Studies of areas where experimental deep-sea mining tests were conducted decades ago have found that the seafloor communities have not recovered, in some cases showing almost no biological recovery decades later. This is the deep-sea equivalent of clear-cutting an old-growth forest that took millions of years to develop, and discovering afterward that it doesn't grow back on any timescale you can plan around. The organisms, as noted in the previous chapter, have no adaptive toolkit for this kind of rapid change, and the ecological functions they perform, including their role in the carbon burial process, don't simply resume when the disruption stops. They stop. There is also the matter of deep-sea fishing, particularly the practice of bottom trawling in deep water, which drags weighted nets across the seafloor and indiscriminately destroys everything in the path of the trawl. This practice has been documented in waters far shallower than the Hadal zone, but its effects reach ecosystems that are still poorly understood and that, as we now know, are performing functions beyond just supporting a local food web. Every time a trawl net scrapes across a deep-sea coral reef or a section of seamount or a patch of biologically active sediment, it is potentially disrupting a carbon processing system that has been running continuously for geological ages. Not because the trawlers intend to interfere with the global carbon cycle, they almost certainly do not think about it in those terms, but because the ocean floor is not the inert geological surface it was assumed to be when these practices were developed. It is a biologically active system with planetary-scale functions, and treating it as a simple substrate for resource extraction has consequences that extend well beyond the immediate harvest. What makes this chapter of the deep ocean story feel almost operatically ironic is the scale of the contrast. The organisms at the bottom of the Mariana Trench are about as far from human daily experience as anything on Earth. They have never seen sunlight. They live under pressures that would kill anything familiar to surface biology in seconds. They reproduce so slowly that a generation spans what might be a human childhood. They are in every measurable way completely disconnected from the world on the surface, and yet they are actively, continuously, and materially contributing to the stability of the atmosphere that makes human civilization possible. They are working in their quiet, unhurried, alien way to keep the planet's carbon cycle balanced. They have been doing this since long before humans arrived and will presumably continue doing it long after, provided we don't disrupt the system before we've fully understood what it's doing. The abyss is not empty, it is not separate. It is not a curiosity at the bottom of a distant ocean that doesn't concern anyone who lives above sea level. It is a functioning component of the planetary system, a long-term carbon storage facility, an ancient biological archive, a pressure-tested evolutionary laboratory, and a living demonstration that the most consequential things on Earth are not always the most visible. The trench doesn't announce itself, it doesn't make headlines, it sits there, in the dark, doing the work, and it has been doing it for longer than we have had words for any of this. At some point in the last few years, someone almost certainly showed you a video of a deep-sea creature glowing in the dark, and your reaction was probably some version of, "That looks fake." It does look fake. It looks like something a visual effects team put together for a science fiction film with a reasonable budget and an interest in making things feel appropriately alien. Pulsing blue jellyfish. Fish with lines of cold white light running along their bodies. Clouds of luminescent particles drifting through black water like a galaxy in miniature. The whole thing has a quality that feels more like art direction than natural history. And yet it is entirely real, entirely biological, and here is the part that keeps researchers up at night in the best possible way. It is the dominant form of visual communication in the largest inhabited space on Earth. More than 75% of deep-sea animals produce bioluminescence. That number is worth sitting with for a moment. 3 out of every 4 animals in the deep ocean are capable of generating their own light. In an environment where sunlight is permanently absent, where the concept of a bright day has never once existed, life did not adapt to darkness by abandoning light as a tool. It did something far more interesting. It reinvented light from scratch, using entirely different chemistry for entirely different purposes, with results that are in several measurable ways more sophisticated than what evolution managed to do with eyes and sunlight on the surface. The darkness didn't end light as a biological resource, it just changed who was in charge of producing it. The chemistry behind bioluminescence is called the luciferin-luciferase reaction, and it works on principles that have nothing to do with heat or combustion, which is why the light produced is called cold light, and why it is so extraordinarily efficient by comparison to any technology humans have built. In standard bioluminescence, a molecule called luciferin reacts with oxygen in the presence of an enzyme called luciferase, releasing energy in the form of photons rather than heat. The efficiency of this conversion is remarkable. Depending on the species, somewhere between 60 and 90% of the chemical energy input gets converted to light, with almost no waste heat generated. For comparison, an incandescent light bulb converts only about 5% of its electrical energy to visible light, with the rest radiating as heat. A standard LED is considerably better, around 30 to 50% efficient, but still falls short of what evolution quietly worked out in the deep ocean over geological timescales. We spent decades and enormous engineering resources developing LED technology, and the end result is still notably worse than what a small translucent shrimp figured out for free. That's a little humbling, if you dwell on it. What makes deep-sea bioluminescence genuinely fascinating beyond just the efficiency numbers is the diversity of its applications. Light, in the deep ocean, is not a single-purpose tool the way sunlight is on the surface. Sunlight just illuminates everything all the time. Deep-sea bioluminescence is modular, targeted and context-specific. Different organisms have evolved it for completely different functions, sometimes multiple functions simultaneously, in ways that make the surface world's relationship with light look comparatively unsophisticated. Counter-illumination is one of the most elegant examples. In the mesopelagic zone, the twilight zone between about 200 and 1,000 meters depth, there is a small but real amount of ambient light coming from above. Not enough to see by, not enough to support photosynthesis, but enough to create a faint silhouette of any animal swimming in the water column when viewed from below. A predator looking upward could detect prey as a dark shape against the marginally lighter water above. Evolution's solution to this, developed independently across multiple lineages, was counter-illumination, producing bioluminescent light on the underside of the body that matches the intensity and colour of the ambient light above, effectively making the animal disappear against the background. Some species even have photoreceptors that sample the ambient light from above and continuously adjust their bioluminescent output to match current conditions. An active camouflage system, biological stealth technology. Running on chemical reactions, maintaining itself autonomously, refined over millions of years. The military spent considerable sums of money trying to develop something roughly equivalent, and the deep ocean had already patented the concept a few 100 million years earlier. Then there is the use of bioluminescence as a lure. The anglerfish is the most famous example, and frankly the anglerfish has earned its notoriety. The females, and in anglerfish it is specifically the females who do the luring, because the males have taken a different evolutionary path that is too strange to fully address here, carry a modified dorsal spine tipped with a luminescent organ, called an esker, which dangles in front of their mouths like a fishing lure in front of a very patient angler. Small organisms attracted by the glow swim toward it in the darkness, presumably operating on the reasonable deep-sea assumption that light sources are worth investigating, and find themselves unexpectedly in proximity to a set of jaws designed for fast, inescapable capture. The anglerfish's mouth is so large relative to its body that it can swallow prey larger than itself, which suggests a creature that doesn't believe in leaving food on the table. It is nature's original bait and switch, perfected over geological timescales, and it works because in an environment with no ambient light, a glowing object is irresistible. It's the biological equivalent of being the only lit sign on a pitch-dark highway. Everything with eyes is going to look. Communication is another application, and probably the most complex one. Many deep-sea fish species produce bioluminescent patterns along their bodies, rows of light-producing organs called photophores, arranged in species-specific configurations. These patterns are used for species recognition, in an ocean where you can't see colour the way surface animals do, and where running into a member of your own species is not a guaranteed event. Having a unique light signature is a useful way to identify potential mates without having to get uncomfortably close to something that might eat you first. Different species have different photophore patterns, different flash sequences, different colours of emission, creating what is functionally a bioluminescent signature system that allows recognition and communication in total darkness. Some squid species can produce rapidly changing light patterns across their entire skin surface, allowing what researchers believe may be complex communication between individuals. A living screen, essentially, capable of displaying information, encoded in light pulses. We have not fully decoded what these displays mean. The vocabulary of deep-sea squid bioluminescence is still mostly a mystery, which is either a gap in current science or an exciting research agenda, depending on how optimistic you're feeling. The bacterial contribution to the deep-sea light show operates on a different model entirely. Bioluminescent bacteria don't necessarily keep their light for themselves. Some of them are deployed by larger organisms as living light sources. The anglerfish's luminescent lure, for instance, is in many species populated by symbiotic bioluminescent bacteria that the fish cultivates in a specialized organ. The fish provides the bacteria with a nutrient-rich environment. The bacteria provide the light, another roommate arrangement with a long-term lease and mutual benefits, which the deep ocean seems to specialize in producing. Bacterial bioluminescence also creates free-floating luminescent clouds in the water column, concentrations of light-producing bacteria that drift and pulse together, creating diffuse glowing patches that can serve simultaneously as camouflage, hiding an organism within a larger luminous context, and as a potential attractant for larger creatures that might then become food for something else. It is ecology encoded in light. The engineering community's interest in bioluminescence is not casual or merely academic. The luciferase enzyme system has already been adopted as a fundamental tool in molecular biology and medical research. It is used as a reporter gene, meaning it gets attached to other genes, so that researchers can track whether those genes are being expressed. Because wherever the gene is active, the organism glows, providing a visual readout of biological activity that would otherwise require complex and expensive analytical procedures. Luciferase-based assays are used in drug development, disease research, and environmental monitoring. The molecule that a deep-sea organism evolved to produce light for hunting or mating became one of the most widely used tools in modern molecular biology. The deep ocean, apparently, has applications it hadn't planned on. Beyond the existing applications, there is active research interest in developing bioluminescence-based lighting systems, not as a mainstream power technology, which faces obvious scaling challenges, but for specific applications where cold, self-contained, chemically powered light would be valuable. Medical implants that need to produce light internally without generating heat. Environmental sensors that can operate without electrical power in remote locations. Display technologies that consume less energy by borrowing the conversion efficiency that evolution already developed. None of these are fully realized yet, but the design principles are all sitting in the deep ocean, available for study, in organisms that evolved them millions of years before the concept of an engineering department existed. What bioluminescence ultimately represents, in the context of the deep ocean story, is a lesson in what happens when a fundamental resource disappears and life decides that the absence is actually an opportunity. Sunlight vanished below 200 meters. Surface logic would suggest that anything dependent on visual communication would simply stop using it. Instead, the deep ocean developed its own light industry, more efficient, more targeted, more ecologically layered than the passive, ambient illumination of the surface world. It built a language out of cold chemistry and evolutionary time, and it has been using that language to hunt, hide, attract, communicate, and navigate in the absolute dark for hundreds of millions of years. We are only beginning to eavesdrop on the conversation. There is a persistent assumption embedded in modern culture that the Earth has been fully explored. Not in the sense that every square kilometre has been visited by a human being, obviously, but in the sense that the basic inventory is complete. We know what's out there. The big things have been found. The spectacular discoveries are behind us, belonging to a golden age of exploration that ended somewhere around the early 20th century, when the last blank spaces disappeared from the maps of the continents. What remains is refinement and detail, filling in the specifics of things already broadly understood. This is, to put it plainly, one of the most confidently wrong assumptions in contemporary scientific culture, and the deep ocean is the most dramatic evidence against it. Less than 25% of the global ocean floor has been mapped to a resolution that would allow you to identify features the size of a house. The rest is known only at the rough low-resolution level produced by satellite altimetry, a technique that infers ocean floor topography from the subtle variations in sea surface height caused by the gravitational pull of underwater mountains and valleys. It works well enough to tell you where a mountain range is. It doesn't tell you what lives on it. For comparison, we have higher resolution maps of the surface of Mars than we do of the floor of our own ocean. This is not a metaphor or a rhetorical exaggeration. It is a straightforward statement of current fact that consistently surprises people when they hear it for the first time, and then continues to bother them once they've had time to think about the implications. The Hadal Zone, the trench environments below 6,000 meters, has received the least attention of any ocean depth category, for reasons that are primarily logistical rather than scientific. Getting instruments to those depths is expensive, technically demanding, and slow. Early deep-sea research used lander systems that had to be lowered on kilometers of cable, left to collect data, and then retrieved. A process that could take the better part of a research cruise's time budget for a relatively small return of information. Modern remotely operated vehicles and autonomous underwater vehicles have improved the situation considerably, but the cost and complexity of Hadal research still means that major expedition opportunities are rare, and the trench systems that have received serious scientific attention represent a small fraction of the total. The Mariana Trench is the most studied Hadal environment on Earth, and even it has been visited by research submersibles only a handful of times in the decades since Piccard and Walsh made the first descent in 1960. What consistently happens when new expeditions do reach unexplored sections of deep trenches is that they find things nobody expected, in numbers nobody expected, doing things nobody expected. This is not a selective reporting of dramatic outliers, it is the baseline pattern of deep-sea discovery. A 2021 expedition to the Mariana Trench returned with specimens and footage documenting multiple species previously unknown to science, alongside organisms from taxonomic groups that had never been recorded at those depths. A survey of the Atacama Trench off the coast of Chile documented an entirely distinct community of Hadal organisms that showed significant differences from the Mariana fauna, suggesting that each trench system is developing its own biological character in isolation, separate evolutionary experiments running in parallel, separated by mid-ocean ridges and thousands of kilometers of abyssal plain, and each one capable of producing surprises. An expedition to the Tonga Trench, one of the deepest in the world and among the least studied, found Hadal fish species at depth ranges that extended current records and organisms with morphological features that hadn't been documented in any related species. The pattern is consistent enough that researchers working in deep trench environments operate with a near certainty that any expedition to a previously unvisited area will produce new species, not might produce, will produce. The question is not whether something new will be found, but how many new things and how unexpected they will be. This is a remarkable scientific situation, one of the only remaining environments on Earth where novelty is essentially guaranteed before you arrive. Most surface ecosystems have been thoroughly enough surveyed that discovering a new vertebrate species is a genuinely rare event, generating scientific papers and news coverage. In the deep Hadal zone, discovering a new vertebrate species would be a solid result for a research cruise, but not a shocking one. Finding multiple undescribed invertebrate species in a single expedition is routine. What kinds of things might be waiting in the unexplored sections? This is necessarily speculative, but informed speculation based on what the explored sections have already demonstrated. The deep ocean has a well-established track record of producing organisms that violate prior expectations about biological possibility at extreme depth. So the most honest answer is that the finds in unexplored territory are likely to extend the current record holders deeper living fish than any currently documented. Invertebrate communities with metabolic and structural adaptations that fall outside any known framework. Microbial ecosystems with biochemical machinery that has no analogue in anything yet studied. Given that every expansion of the explored area has added new chapters rather than simply filling in existing ones, there is no scientific basis for expecting the pattern to reverse. The unexplored sections of the Hadal zone are not likely to be less biologically interesting than the explored ones. If the pattern holds, and there is no reason to think it won't, they are likely to be more so. There is a specific area of the Mariana Trench system that researchers have flagged as particularly high priority for future investigation: the hydrothermal and cold seep environments that exist at various points along the trench walls and floor, some of which have been identified through indirect evidence but never directly explored. We know from the hydrothermal vent discoveries discussed earlier that these environments support distinct ecosystems built on chemosynthesis, rather than the marine snow food supply that most Hadal organisms depend on. If similar vent environments exist within the Hadal zone itself, combining the extreme depth conditions with the chemical energy of active venting, the resulting ecosystems would be under selection pressures that combine two of the most extreme environments on Earth simultaneously. Nobody has fully characterized what lives there. Nobody has visited most of these sites. The biology they support is currently entirely unknown. Whatever is there has been developing in isolation, under unique conditions for potentially millions of years without any human observation. That is, by any reasonable definition, one of the most significant unexplored biological environments on the planet. The technology for exploring these environments is advancing, but not quickly enough to satisfy the scientific community's ambitions. Next-generation autonomous underwater vehicles are being developed with the depth ratings and operational endurance to conduct extended surveys of Hadal environments without requiring continuous ship support, which is the single largest logistical bottleneck in deep-sea research, because research ship time costs approximately the same as chartering a moderately sized private jet and running it continuously. These autonomous systems won't replace human-operated submersibles for the most detailed work, but they will make systematic surveys of large unexplored trench areas feasible in a way that current technology doesn't support. When those surveys happen, the biological inventory they return will almost certainly require significant updates to what we currently think we know about deep ocean life. Based on past form, significant updates is probably an understatement. There is also the matter of the other deep trenches beyond the Mariana: the Tonga, the Philippine, the Kermadec, the South Sandwich, the Puerto Rico Trench in the Atlantic, the Java Trench in the Indian Ocean, among others. Most of these have received only fragmentary scientific attention. The Kermadec Trench in the South Pacific is one of the longest in the world and has been the subject of enough sampling to confirm that its fauna is distinct from the Marianas, with different dominant species and different community structures. The Puerto Rico Trench, the deepest point in the Atlantic at about 8,400 meters, has been visited so infrequently that its biological community is known only in the broadest outlines. Each of these represents a separate deep ocean laboratory, running its own evolutionary experiments under its own specific conditions, and most of them remain essentially unread. The number of species currently catalogued from hadal environments globally is almost certainly a small fraction of the species that actually exist there. Estimates suggest we may have formally described somewhere between 10 and 20% of hadal species, which means somewhere between 80 and 90% of the biological diversity at those depths has not been encountered, named, or studied. Think about what that number means in context. The hadal zone is not a marginal or trivial environment. It occupies the deepest portions of ocean systems that cover more than 2/3 of the Earth's surface. It hosts organisms with biological adaptations found nowhere else on the planet. It performs ecological functions with global climate implications, and somewhere between 80 and 90% of its species are unknown. If you applied that ratio to the Amazon rainforest, the scientific community would consider it a crisis-level gap in our understanding of life on Earth. For the hadal zone, it is just the current baseline. The map of life on Earth is genuinely, substantially incomplete, not in the sense that there are a few footnotes missing, but in the sense that entire chapters haven't been written yet. The most radical biological discoveries of the last 50 years, chemosynthesis, extremophil diversity, the metabolic range of microbial life, came from environments that were assumed to be biologically uninteresting before anyone bothered to look carefully. The deep trenches, which we have barely looked at, have every reason to contain discoveries of equivalent or greater magnitude. The biology of the hadal zone doesn't operate by rules developed from surface observations. Every expedition has confirmed this. There is no reasonable scientific argument for assuming the next expeditions will be different. The age of biological exploration is not over, it relocated. It moved to places that are colder and darker and more expensive to reach, and it is still actively producing the most surprising findings in the field. Every blank space on the map of the deep ocean floor is a question mark, and question marks in this environment have a strong historical tendency to resolve into something extraordinary. The only thing we can say with confidence about what's waiting in the unexplored trenches is that it will not match whatever we expected to find there. It never has. For most of human history, the question of whether life exists elsewhere in the universe was essentially a philosophical one. There was no scientific framework for answering it, because the only data point available was Earth, and drawing conclusions about the universe from a single example is not exactly a robust methodology. Life exists here, the planet has certain conditions, therefore life requires those conditions. That was more or less the entirety of the reasoning available. And those conditions, as understood for most of scientific history, were fairly specific. Liquid water, moderate temperatures, sunlight as an energy source, the right chemical building blocks. Look for planets with those features, the logic ran, and you'd be looking in roughly the right direction. Everything else was probably barren. Then we found the hydrothermal vents. Then we found the hadal organisms. Then we found the microbial communities reproducing once per decade in sediment layers hundreds of millions of years old. And the list of required conditions for life quietly but dramatically shrank. This matters enormously for the search for extraterrestrial life, because the conditions we were originally looking for, moderate temperatures, sunlight, a pleasant Earth-like surface, are relatively rare in the solar system and apparently quite uncommon in the universe at large. Most of the universe is cold, dark, and either airless or covered in clouds of the wrong chemistry. Earth-like surface conditions are the exception, not the rule. But geological heat, liquid water under pressure, chemical energy gradients, those are much more widely distributed. They don't require a star at the right distance. They don't require a stable surface or a breathable atmosphere. They require a geologically active body with enough internal heat to maintain liquid water somewhere beneath its surface, and that description fits several objects in our own solar system that used to be filed confidently under definitely not. Interesting from a life perspective, Europa is the one that gets the most attention, and for good reason. Europa is one of Jupiter's 4 large moons, about the size of Earth's moon, and it is covered in a shell of ice. Underneath that ice, and this was confirmed by the Galileo spacecraft in the 1990s through measurements of Europa's magnetic field, is a global ocean of liquid salt water. Not a lake, not a pocket of water. A global ocean containing roughly twice the volume of all of Earth's oceans combined, sitting under an ice shell estimated to be between 15 and 25 kilometers thick. It has been liquid for billions of years. The heat source is not the Sun. Europa is about 780 million kilometers from the Sun, which is not a neighborhood known for warm temperatures. The heat comes from tidal flexing. Jupiter's immense gravitational field continuously squeezes and stretches Europa as it orbits, generating heat through friction in the moon's rocky interior. That heat keeps the water liquid. It also almost certainly drives geological activity on the seafloor, and geological activity on the seafloor means chemical energy gradients, and chemical energy gradients mean hydrothermal vents are plausible, and hydrothermal vents, as we have now, thoroughly established, mean life is not out of the question. The parallel to the Mariana Trench environment is not loose or metaphorical, it is quite specific. Europa's subsurface ocean is cold, probably near freezing at the ice interface, and warmer near the seafloor if geothermal activity exists there. It receives no sunlight, it has liquid water. It has chemical interactions between the water and rocky seafloor material that would produce the kinds of reduced compounds, hydrogen sulfide, molecular hydrogen, various minerals, that chemosynthetic bacteria here on Earth use as energy sources. If you designed a habitat specifically to match what works in the deep ocean, and then built it somewhere else in the solar system, you would end up with something that looks a lot like the interior of Europa, which either tells you that Europa is a plausible habitat for life, or tells you that the conditions we previously thought were required for life were badly miscalibrated. Either way, the deep ocean changed the conversation. Enceladus, a small moon of Saturn about the diameter of the United Kingdom, may be the most exciting object in the solar system for astrobiologists right now, and its story has the advantage of not requiring any inference or theoretical calculation. We have direct evidence of what it's doing. In 2005, NASA's Cassini spacecraft flew through the plumes of material being ejected from fractures near Enceladus's south pole, and later analysis of those plumes found water vapor, ice particles, molecular hydrogen, silica particles consistent with hydrothermal chemistry, and organic compounds including some complex ones. Molecular hydrogen in particular is a significant finding, because molecular hydrogen is produced when hot water reacts with rock at hydrothermal vents, the same reaction that drives chemosynthesis in Earth's deep ocean. The implication is that Enceladus has active hydrothermal systems on its seafloor right now, continuously, underneath its ice shell and inside its interior ocean. This is not a guess. The evidence for it came through at spacecraft velocity and got analysed by some of the sharpest planetary scientists on the planet. Enceladus is doing hydrothermal chemistry. It has been doing it long enough and at sufficient scale to eject the products into space where a passing spacecraft could sample them. Whether anything is living off that chemistry is the question for the next generation of missions, but the conditions that would allow it to are demonstrably present. The scientific importance of the Mariana Trench in this context is that it functions as what researchers sometimes call an analog environment, a place on Earth where conditions approximate those expected elsewhere, allowing detailed study of biology and chemistry that could inform the search for extraterrestrial life. When mission planners at NASA and the European Space Agency think about what instruments to send to Europa or Enceladus and what signatures to look for, they draw heavily on what has been learned in Earth's deep ocean. The chemical signatures of chemosynthetic life, the physical textures of hydrothermal mineral deposits, the specific compounds produced by microbial communities living at high pressure and low temperature, the range of biological adaptations that have evolved for these conditions. All of that knowledge comes from research in deep ocean trenches and hydrothermal vent systems, and it is directly applied in designing the science payloads for future missions to icy moons. There are also other candidates in the solar system that have joined the discussion as understanding of subsurface oceans has expanded. Ganymede, another of Jupiter's moons and the largest moon in the solar system, almost certainly has a subsurface ocean sandwiched between layers of ice. Callisto, the outermost large Jovian moon, may have one as well. Titan, Saturn's largest moon, has a dense atmosphere and surface lakes of liquid methane, a completely different chemistry from water-based life, but one that some researchers argue could support a different kind of biochemistry entirely. Pluto, on the basis of the New Horizons flyby data, may have had a subsurface ocean in its past, possibly still has one deep below its surface, and has more complex surface chemistry than anyone expected before the flyby. The solar system, it turns out, is substantially wetter and more geologically interesting than the picture developed from telescope observations in the 20th century suggested. Liquid water, in various forms and locations, is not rare. It is common, and everywhere we find liquid water in contact with geothermal heat and chemical gradients, we now know, thanks to the deep ocean, that we cannot confidently say life is absent. The implications for the search for life beyond the solar system are even more expansive. Exoplanet astronomy has identified thousands of planets outside our solar system, and the search for habitable ones has historically focused on the habitable zone, the range of orbital distances from a star where liquid water could exist on a planetary surface. These are the Earth-like candidates, the ones that got the most attention in early discussions of extraterrestrial life. But subsurface oceans don't need a habitable zone. They need internal heat, which can come from radioactive decay in a planet's rocky interior, from tidal heating from a large nearby planet, from residual formation heat in young planets, from various other sources that have nothing to do with the planet's distance from its star. This means the population of potentially habitable environments in the universe is vastly larger than the habitable zone calculation suggested. It includes ice-covered ocean worlds orbiting far from their stars. It includes moons of gas giants in the cold outer reaches of solar systems. It includes objects that would have been written off as dead and frozen by the pre-1977 understanding of life's requirements. The Mariana Trench and the organisms it contains didn't just add a data point to astrobiology. They restructured the entire framework of what counts as a plausible habitat. There is something appropriately humbling about the chain of reasoning that starts with two men climbing into a steel ball in 1960 and ends with a fundamentally revised estimate of the number of potentially inhabited worlds in the universe. Nobody planned this. Nobody sat down and said, "Let's study the deep ocean because it will teach us about the likelihood of life on Europa." It happened because people were curious about a place, pointed instruments at it, and let the data change their thinking. And the data, predictably, was more interesting than anyone had expected. It has been more interesting at every step. The organisms in the Hadal zone, the chemosynthetic ecosystems at hydrothermal vents, the ancient microbes in the sediment, the bioluminescent language systems, the extraordinary molecular adaptations, none of these were predicted. All of them changed what we thought was possible. The practical consequence of all this expanded possibility is a generation of space missions in various stages of planning, development and execution that are aimed specifically at the icy moon targets. NASA's Europa Clipper mission launched in 2024 and will arrive at Jupiter in the early 2030s, conducting detailed flybys of Europa to characterize its ocean and look for signs of habitability. The European Space Agency's JUICE mission, Jupiter Icy Moons Explorer, is en route to the Jovian system to study Europa, Ganymede and Callisto. A dedicated Enceladus mission has been identified as a high priority by the planetary science community's decadal survey, the process by which the scientific community collectively decides what it most wants to explore next. These missions will not answer the question of whether life exists on icy moons, that will require landing on them, drilling through the ice, or sampling the ocean directly, which is a generation of engineering work away. But they will determine whether the conditions for life as we understand it from the deep ocean are present, which will refine the question considerably. The Mariana Trench, in this context, is not just the deepest place on Earth. It is the field training ground for one of the most significant scientific investigations in human history. Every extremophile characterized, every hydrothermal ecosystem mapped, every chemosynthetic metabolic pathway sequenced, every pressure-adapted protein structure determined, all of it contributes to a scientific toolkit that will eventually be pointed outward at places hundreds of millions of kilometers away, looking for signs that the pattern we found in our own ocean floor is not unique to Earth. Based on everything the deep ocean has taught us so far about what life is capable of, the smart money is not on disappointment. We started this journey with a simple premise: the deepest place on Earth had to be worth understanding. And what we found, working through every layer of the story, is that worth understanding might be the understatement of the geological era. The Mariana Trench isn't a geographical curiosity that impressed explorers and then went back to being irrelevant. It turned out to be the place where almost everything we thought we knew about life, what it needs, what it can withstand, where it can go, how long it can last, got systematically and decisively corrected. Think about the chain of surprises. We assumed the deep ocean was sterile. It wasn't. It was swarming. We assumed life needed sunlight. It didn't. It built its own energy economy out of geothermal chemistry and ran it for hundreds of millions of years without sending anyone a memo. We assumed pressure like that was universally lethal. Organisms down there use it as a zoning permit, exploiting the very conditions that would destroy surface life as a tool for keeping competitors out. We assumed ancient sediment was a graveyard. It's a living library, holding microbes that predate the dinosaurs and haven't changed enough to notice several mass extinctions along the way. We assumed the deep ocean was disconnected from the atmosphere. It's actively regulating the carbon cycle that determines whether the surface remains habitable. And we assumed, for most of human intellectual history, that life was a local phenomenon. Earth's peculiar trick, probably unique, probably dependent on conditions so specific they couldn't be replicated elsewhere. Then the deep ocean showed us what it takes to actually sustain life, and the list turned out to be short enough to fit on an index card. Liquid water, chemical energy, stability, that's most of it. And those conditions exist on at least 2 moons in our own solar system right now, in environments that look remarkably similar to the floor of the Mariana Trench. The emotional weight of that chain of discoveries is something worth sitting with for a moment, because it isn't just interesting in the scientific sense. It is philosophically transformative in a way that doesn't get acknowledged often enough. Humans have a long history of assuming they occupy a privileged position in the universe, the Earth at the center, the sun circling us, complex life as the obvious endpoint of biology, intelligence as the inevitable product of evolution given the right conditions. And every time we have made that assumption, and then looked more carefully, the universe has corrected us with something between gentle patience and aggressive indifference. The Copernican correction, the Darwinian correction. The cosmological correction that revealed we live on a small rock, orbiting one of several hundred billion stars in one of several hundred billion galaxies. Each of these corrections was initially uncomfortable, and eventually became just part of what it means to know things accurately. The deep ocean corrections are in the same category. Life doesn't need us, doesn't need our sunlight, doesn't need our moderate temperatures or our oxygenated surface or our comfortable pressure. Life, it turns out, is far less fragile and far less particular than we ever gave it credit for being. This is, depending on how you look at it, either deeply reassuring or deeply unsettling, and the honest answer is that it's both simultaneously. Reassuring because it means the universe is probably far more biologically inhabited than the pessimistic estimates suggested. Unsettling because it removes any remaining basis for treating Earth's surface biosphere as special in the sense of being uniquely capable of supporting life. It is special, enormously, irreplaceably special, but for reasons that have more to do with the particular evolution that happened here, the specific organisms that developed here, the complex ecosystems that took billions of years to assemble. Here, not because it's the only kind of place that works. There are other kinds of places that work. We found one several miles below our own feet. There is also something worth acknowledging about what the Mariana Trench story says about the practice of science itself, and about curiosity as a fundamental value. Nobody sent the Tris to the bottom in 1960 because they expected to find anything commercially valuable. Nobody funded the hydrothermal vent expeditions in 1977 Because there was a clear return on investment attached to discovering a new energy metabolism. The research was done because people wanted to know what was there. Because the question, what lives at the deepest point of the ocean, was interesting enough on its own terms to be worth the engineering effort and the risk. And the answer, which couldn't have been predicted from any prior framework, turned out to restructure our understanding of biology, inform the design of space missions, provide new tools for molecular research, and raise the estimated likelihood of life in the universe by a number that nobody had a methodology for calculating in 1959. Pure curiosity, applied carefully and patiently, produced practical and philosophical consequences that dwarf almost any targeted research program from the same era. This is not an argument against applied research. It is an argument for not letting the emphasis on immediate applications crowd out the kind of investigation that starts with, "I wonder what's down there," and ends with rewriting the textbooks. The Mariana Trench is also, and this part tends to get lost in the biological excitement, a reminder of how much planet we still have left to understand. The deep ocean is not the only substantially uncharted territory on Earth. Cave systems, deep aquifers, isolated ecosystems in extreme environments across the globe all hold biological and geological surprises that surface science hasn't fully catalogued. But the deep ocean is the largest, the most biologically active and the most consequential piece of unexplored territory on the planet, and its proximity to human civilization, right here, right below the surface of an ocean we sail across in cargo. Ships and vacation liners, makes its relative neglect genuinely remarkable. We have spent more effort mapping the surface of the moon than we have mapping the floor of our own ocean. We can tell you more about the geology of Mars than we can about the Hadal environments at the bottom of the Pacific. That gap isn't a minor administrative oversight in the history of exploration. It is a standing invitation, and the organisms currently living in the Mariana Trench are, in their completely indifferent way, waiting for us to take it more seriously. Because here is what every chapter of this story points toward. We are not done being surprised, not even close. The biological inventory of the Hadal zone is estimated to be somewhere between 10 and 20% complete. The hydrothermal and cold seep environments within the trench walls have barely been visited. The chemistry of the deep sediment communities is understood in outline but not in detail. The genetic diversity of Hadal microbial communities is only beginning to be characterized through modern sequencing technology. And all of that is just the Mariana Trench. The Tonga Trench, the Kermadec, the Puerto Rico, the Java, each one a separate evolutionary laboratory, each one operating in isolation for millions of years, each one probably harboring organisms and adaptations that will again expand what we thought was possible when someone finally gets there with good enough instruments. The honest conclusion from everything we've covered isn't a neat summary that ties it all together. It's something more like a recalibration of what life is, of where it can be, of how long it can persist and under what conditions and with what remarkable ingenuity, of how connected the most remote and extreme environments are to the stability of everything we depend on at the surface, and of how much of the planet we are still only beginning to understand, which is simultaneously embarrassing given how long we've been here, and exciting given what the first round of looking has already turned up. The trench doesn't care about any of this, obviously. It has been sitting there in the dark at 11 kilometers below sea level, getting on with things, since before there was anyone capable of being curious about it. The amphipods are still swarming over whatever organic material arrived this week. The ancient microbes in the sediment are completing whatever generation they started working on a decade ago. The pressure-adapted fish are hunting in total darkness, using biological systems that took millions of years to develop, and that engineers are still trying to replicate. Everything down there is continuing exactly as it was before we knew about it, and will continue exactly as it is after we finish talking about it. But we know about it now. And what we know has already changed the map of life, of this planet, and of what we're looking for when we point our spacecraft outward and ask, for the first time with genuine scientific grounding, whether we're alone. That question used to be philosophical. The deep ocean made it empirical. That is what it means to go looking at the bottom of the world, and why, the deeper we go, the more clearly we understand that we have only just started asking the right questions. If this one got you thinking, and if you made it all the way to the end, it clearly did, smash that like button. It genuinely helps more than you'd think. Subscribe if you want more dives into the parts of the world that most people walk right past without noticing, and drop a comment. What part of this story changed something for you? What did you not expect to hear? I read every one of them. See you in the next one.